Welcome to Lab 2, everybody. Today we are looking at bending in beams and particularly how changes in cross-sectional dimensions or cross-sectional configurations affect the bending response of beams. So I've printed off two different beams. One is a beam with a rectangular cross-section, and the other beam is a channel section. Now, the cross-sections of these beams have been designed so that if printed 100% accurate to the solid models, both of those beams would have equal cross-sectional areas. But as we'll see, the response to bending is quite a bit different between those two beams, even though they have equal cross-sectional areas. And that's because the moment of inertia of those cross-sections about the horizontal axis is very different. So I'm going to get our test set up in terms of the loading apparatus and the first beam loaded in, and then I'll show you what that all looks like. So here's the loading setup that we have for these beam tests here. Within the top grip, we've got a flat plate that is going to apply a load. So the crosshead's going to move downwards, pressing this flat plate onto our beam here. And that flat plate from one side to the other side has a width of 50 millimeters. So that is the length over which the applied load is going to be distributed upon the beam. Then we've got a loading frame here to support our beam. And during the test, we'll be recording force from the load cell and displacement of the crosshead. So the force is the total force that's being applied over that plate, and the movement of the crosshead is going to give vertical deflection of the beam. Now, the length of the beam, what is important here is the unsupported span length. So that's from one side of the support to the other side of the support here. And that distance is 235 millimeters. So 235 millimeters of unsupported span. Okay, so we're all set to begin the test now. And one other thing you'll note is that I've made little black marks on the beam here and there so that you can see how the beam moves relative to the support. And that will give you a sense of how you should model the supports for this beam. So I'm going to move the crosshead down into position here, almost contacting, but not quite contacting the beam. Okay, there we go. So it's just about touching now. And I'm going to zero the force from the load cell. So we start with zero load. And then we'll begin the test. Okay, so we're running now, and we've got a live graph of force versus crosshead displacement. And you can see the force increasing now as we've made contact with that beam. Now we've got a nice linear response between force and displacement that's developing on our graph. So deflection's a bit over 16 millimeters now. So 19 millimeters of deflection, and we're just sort of approaching a load of 400 newtons of applied force. And you can see that we're starting to get a very significant deflection in that beam. You can also see that our markers that we added, those black markers, have started to move away from the supports a little bit there. So we've got some horizontal translation going on between the beam and the supports. So that tells you something about what sort of supports you would model this beam as having. Now, in this configuration, that beam is quite flexible, so there's a chance that before this beam actually breaks, it will just slip out of those supports. But we'll see. We're starting to see now quite a decrease in the slope of that force deformation curve. And now the force deformation curve is having little increases and dips in it, and that is as the beam starts to slide more and more against those supports, and it does sort of a slide, a slip stick type motion. And on the left-hand side, we're going to pop out of that support at any moment now before the beam actually breaks. Okay, so the beam's popped out. So let's stop this test now and we'll load up the channel section and see how that compares. Okay, so the channel beam's loaded up now, and I'll just remove this for a second to show you the orientation. So we're loading it in that orientation there. So I'll put that back in and just make sure it's nicely centered there. And now we'll bring the crosshead down to just almost make contact with that, the top of that beam there. Okay, just about making contact there. Now we'll make sure that the load is zeroed. So we're starting from zero applied force. And now we can start the test. So crosshead is now moving. Okay, so now the loading plate's made contact with the beam. Now remember, for the last beam, we reached an applied force of 400 newtons, and it took 20 millimeters, over 20 millimeters of displacement to have that happen. We are now approaching 400 newtons, there we go, at only 4 millimeters of displacement. So you can get an appreciation of just how much stiffer this beam is than the other beam. Now, both beams are made out of PLA plastic, so they both have material that has the same modulus of elasticity, but the beams themselves have very different stiffnesses. And we often hear people use the word stiffness as a substitution for modulus of elasticity, but it's important to realize that modulus of elasticity is a material property, whereas stiffness is a property of a structure or object. Now we're up at approaching 1500 newtons now, and we're getting a decrease in the slope of the load deflection curve. And you can see maybe some whiteness developing in the PLA at the bottom there, concentrated. There we go. I was going to say concentrated under the right edge of that support, and that is indeed where fracture has happened. Okay, so I'll stop this test now, and what I'll do is I'll give you the load deflection data for both of those beams, and you can calculate what the moment of inertia was for each beam, and then look at how that compares to the stiffness of each beam, which is the slope of that load deflection curve. Okay, thanks for watching, and I'll see you again for Lab 3.